4 billion years ago, if you had stood on a Martian plateau, you might have heard the sound of running water. Not the wind howling across a barren desert like today, not the near-total silence of an almost dead planet, but rivers cutting through rock, rain falling onto lakes, thick clouds drifting beneath a sky far warmer than it is now. Mars was once a different world. It is smaller than Earth, about half the diameter, but in its early days, its core was hot and dynamic. A strong magnetic field surrounded the planet, forming an invisible shield against the solar wind. Its atmosphere was much thicker than it is today, trapping enough heat for liquid water to exist on the surface. Orbital data reveal traces of branching valleys that resemble river systems. Not a single river, but entire complex hydrological networks, similar to what we see on Earth. In the Northern Hemisphere, many scientists believe a vast ocean once existed, possibly covering nearly a third of the planet, hundreds of meters deep. If all the water that once existed were gathered together, it would be enough to cover the entire planet in a global ocean more than 100 meters deep. But Mars carried a fatal weakness: its small size. Its core cooled faster than Earth's. The convection of molten metal slowed. The magnetic field weakened and eventually vanished. When that invisible shield collapsed, the solar wind began stripping away the atmosphere directly. Molecule by molecule, it was blown into space over hundreds of millions of years. Pressure dropped. Temperatures fell. Liquid water became unstable. It either froze into permanent ice or evaporated and escaped into space. Mars did not die in a sudden catastrophe. It died by the slow erosion of the cosmos. Today, its atmosphere is only about 1% as thick as Earth's. It is composed mostly of carbon dioxide. If you removed your helmet there, you would lose consciousness within seconds due to lack of oxygen, and the low pressure would cause bodily fluids to begin boiling at body temperature. The average temperature is around -60 degrees Celsius. In winter at the poles, it can drop below -125 degrees. Yet one remarkable fact remains. Mars has a day and night cycle similar to Earth's. A day lasts 24 hours and 37 minutes. It also has seasons, because its axial tilt is about 25 degrees, nearly the same as Earth's. But Mars's axial tilt is not stable like Earth's. Without a large moon to stabilize it, height of the tilt can vary dramatically over millions of years. At times, the tilt increased significantly, causing polar ice to melt and redistribute across the planet. These extreme climate cycles may have created brief warm periods throughout its otherwise cold history. The present surface of Mars is a map of geological extremes. Olympus Mons, the tallest volcano in the solar system, rises nearly 22 kilometers high and is wider than the state of Arizona. Without plate tectonics like Earth's, lava kept piling up in one place for hundreds of millions of years, building a structure so enormous that the horizon curves along its slopes. Valles Marineris stretches more than 4,000 kilometers, nearly the width of the United States, and plunges up to 7 kilometers deep. If placed on Earth, it would swallow Europe. But Mars is not entirely inert. NASA's InSight lander detected Marsquakes, Martian earthquakes, some stronger than expected. This suggests the planet's interior is still active. Recent studies even indicate volcanic activity may have occurred just a few million years ago, almost recent in geological time. At the North and South Poles, the ice caps contain not only frozen water, but also seasonal carbon dioxide ice. In winter, atmospheric CO2 freezes and falls onto the surface. When spring arrives, it sublimates violently, producing gas jets that erupt like small explosions, carving dark patterns into the white ice. Beneath the surface, orbital radar has detected thick layers of ice. If all that ice were to melt, the red planet could once again host oceans, but only in theory, since the current atmospheric pressure would not allow liquid water to persist for long. Then there are its two tiny moons, Phobos and Deimos. Phobos orbits extremely close to Mars and is gradually spiraling inward. In about 30 to 50 million years, tidal forces will tear it apart, potentially forming a temporary ring around the planet before the debris rains down onto the surface. A violent future awaits. Mars is not merely a planet that lost its potential for life. It is a system still evolving. Meteorites from Mars have fallen to Earth, blasted off its surface by ancient impacts. Some samples contain microscopic structures that have fueled decades of debate. No definitive evidence. But the story does not end there. Because the most haunting thing about Mars is not that it is cold. It is that it once had all the fundamental ingredients Earth had when life began. Water, energy, minerals, time, a rocky planet orbiting the same sun. And then, through a quiet chain of changes lasting hundreds of millions of years, it became the red desert we see today. The question is not only what happened to Mars, but this: if it once happened to a world like ours, could it happen to us again? If Mars once held a secret, that secret does not lie exposed among its red stone plains. It lies in details too small for the human eye to see. In molecular structures, in isotopic ratios, in atmospheric fluctuations so thin they are almost non-existent. And to search for them, humanity has sent tireless machines. In 1976, 2 Viking landers touched down on the red planet with a bold objective: to perform direct biological experiments. They mixed Martian soil with nutrient solutions and observed the reaction. The initial results resembled metabolic activity. Yet other measurements failed to detect clear organic compounds. At the time, science did not yet have the tools to resolve every possibility. The debate lasted for decades and has never been fully closed. After Viking, the strategy changed. Instead of trying to prove life existed, sudden missions began laying the groundwork. What kinds of environments could support life? Spirit and Opportunity did not carry complex laboratories, but they achieved something crucial. They demonstrated the existence of watery environments through minerals formed under wet conditions. Hematite spherules, chemically altered rock layers. These were signs of long-term interaction between water and stone. Curiosity went a step further. It carried a miniature chemical laboratory capable of heating soil samples and analyzing the gases released. In ancient rock layers, it detected stable organic compounds, carbon-based frameworks that can survive for billions of years. Not evidence of life, but fundamental ingredients upon which life could be built. Then came methane. Instruments aboard Curiosity recorded seasonal fluctuations in methane levels. Such methane is not stable in the Martian atmosphere. It is broken down by radiation. So if methane continues to appear, it must be produced or released relatively close to the time of detection. The source could be geochemical reactions underground. It could also involve microorganisms. At present, there is no final conclusion, but the existence of a methane cycle remains an unresolved question. In orbit, Methane observed the upper atmosphere and measured how particles are stripped away by the solar wind. The data showed that atmospheric escape is still occurring, albeit slowly. This confirmed a specific physical mechanism, not merely a hypothesis. Perseverance was designed with a different goal: to select and store samples for return to Earth. It drills rock cores, seals them inside airtight titanium tubes, and deposits them on the surface for a future mission to retrieve. These sample tubes represent the possibility of analysis using the most advanced instruments humanity possesses, tools no rover could ever carry. At the same time, InSight measured seismic activity to understand the planet's deep internal structure. The vibrations were analyzed to determine the size and state of the core, mantle, and crust. For the first time, Mars's internal structure was mapped using direct data rather than inference. Orbital satellites use spectrometers to map hydrated minerals, minerals that form only when water participates in chemical reactions. They have also detected perchlorate salts in the soil, compounds that can influence organic chemistry and must be considered when assessing the potential survival of microorganisms. Beyond NASA, other agencies have joined the effort. The UAE's HOPE probe observes the global atmosphere, tracking seasonal variations. China inserted Tianwen-1 into orbit and landed the Zhurong rover to survey terrain and minerals. Europe has been developing deep drilling technologies aimed at reaching soil layers less damaged by radiation. Mars is no longer a single-point investigation. It is a multi-layered observation system: surface, subsurface, lower atmosphere, upper atmosphere. Yet the greatest challenge is not collecting data. It is interpreting it correctly. A structure that resembles a fossil may simply be a self-formed mineral. An organic molecule may have arrived via a meteorite. Methane may originate from reactions between rock and water, without the need for life. Every signal has multiple possible explanations. For that reason, the standard of evidence is set extremely high. No claim is accepted unless it withstands multiple independent tests. The machines on Mars do not have the luxury of being wrong. A single inaccurate conclusion could misdirect an entire field of research for years. This search is not loud. It unfolds slowly, through numbers, through spectra of light, through radio signals traveling hundreds of millions of kilometers. And in that patience, each piece of the puzzle is being placed into position. We have not yet found definitive evidence of life, but we are building an increasingly detailed record of the red planet's environment, chemistry, and evolutionary history. And when the first samples are brought back to laboratories on Earth, the story may enter an entirely new chapter. There will come a moment in the not-so-distant future. A hatch opens, sunlight, fainter than on Earth, spills in. Red dust drifts through the air, and for the first time in history, a human being steps onto the surface of another planet. Not a robot, not a metal arm, a real heartbeat. But to reach that moment, the journey through deep space, lasting 6 to 9 months, is a true test of survival. In microgravity, muscles atrophy, bones lose density, the immune system changes. Astronauts must exercise for hours each day just to prevent their bodies from deteriorating. And when they arrive, the challenges are not over. Mars has only 38% of Earth's gravity. That affects blood circulation, the vestibular system, and even how the brain processes motion. Current research still does not fully know how the human body would respond to living for years in such an environment. Then there is cosmic radiation. Without a strong natural magnetic shield, humans would be exposed to high-energy particles capable of penetrating metal and living tissue. Future-based designs propose burying habitats beneath Martian soil or using the soil itself as shielding. Energy is another complex problem. Sunlight on Mars is about 40% weaker than on Earth. Solar panels must be larger and more efficient. or combined with compact nuclear power sources. Every watt of electricity will be precious. Water, oxygen, fuel, all must be produced locally. The concept of living off the land is known as ISRU, in situ resource utilization. Experimental devices have demonstrated the ability to extract oxygen from atmospheric CO2. Subsurface ice can be melted and purified. Even methane, rocket fuel, can be synthesized from carbon dioxide and imported hydrogen. If these processes function reliably, humans may not only visit and return, they may stay. From there, another vision emerges: colonization. Not cities with blue skies and forests overnight, but sealed modules, pressurized corridors, greenhouses growing crops in controlled environments. Hydroponic agriculture, nearly 100% water recycling, miniature artificial ecosystems. But colonization is not only a technical challenge. It is an ethical and philosophical question. If we build the first city on Mars, are we expanding life or invading a unique natural laboratory? If one day indigenous microorganisms are discovered, would we stop? There are even bolder proposals: thickening the atmosphere by releasing greenhouse gases trapped in the soil, using giant orbital mirrors to warm the surface, even triggering controlled nuclear reactions to alter regional temperatures. Yet current models suggest that the remaining CO2 on Mars may not be sufficient to create Earth-like atmospheric pressure, even if fully released. So if humans live there, they may have to accept life under domes indefinitely. Mars is also a stepping stone to deeper ambitions. Its weaker gravity means launching spacecraft from its surface requires less energy than from Earth. A Martian base could become a staging point for missions farther into the solar system. And as multiple nations set their sights on the red planet, the story becomes not only scientific, but geopolitical. Who arrives first? Who controls resources? Current space treaties state that no nation can claim ownership of a celestial body, but the reality of resource utilization may prove far more complex. In all these scenarios, one truth is clear: Mars is no longer a distant dream. It is a concrete objective within this century's plans. Yet the most compelling aspect is not the technology or the ambition. It is the moment humanity looks back at Earth from another planet. From the surface of Mars, Earth will appear as a faint blue star against the blackness. All of human history, wars, art, love, memory, compressed into a single small point of light. Mars forces us to rethink our place in the universe. It is not only a question of whether life once existed there. It is whether we are mature enough to step beyond our home planet without repeating our old mistakes. When you look up at that red dot in the night sky, what do you see? A place to explore? A land to survive on? Or a test for an entire civilization? Share your thoughts in the comments below. If you had the chance, would you be willing to leave Earth to live on Mars?